talk about the test first. The first thing I would like to say is overall the scores were good, but I know not everybody got the score you would like. So remember this, first of all. You get to replace one score with your final, you know. So if you make it to all the exams and you weren't happy with this one, it doesn't even have to show up in your grade, you know, and you can just think of this as like this test was sort of calibrating your sense of like how the practice problems relate to the exam, you know. But the material on this test, you know, everything's cumulative, so you're responsible for this material on every test, and this material, understanding this stuff is going to be important for going into two-dimensional kinematics. So I think you should, you know, take the time to make sure you understand how to do these problems. I don't know. Should we just go through the whole test, or is that? Yeah? Maybe we should. Okay, so the first question, a rock is dropped from a bridge and takes 1.4 seconds to hit the water. And we're trying to figure out this height. First thing we're going to do is make these four choices. Time equals 0, time final, position equals 0, and positive direction. I'm going to call my 0 the level of the water, and my positive up. The time equals 0 is going to be the instant that it's released. Time final is going to be the instant it hits the water. P equals 0 is going to be the water, and the positive direction is going to be up. And then we can list out the variables we know and want. It takes 1.4 seconds to hit the water, so we know TF is 1.4 seconds. The acceleration is negative 9.81 meters per second squared. The initial position, that's what we're trying to figure out. We know that the final position is 0. So PF is equal to 0. At time equals 0, the object's being dropped, and it's being dropped from a bridge, which is stationary. So V initial is equal to 0. And V final, we don't know and we don't care. And the equation that works with all of this stuff is PF is equal to PI plus VITF plus 1/2 ATF squared. So 0 is equal to pi plus, since vi is 0, this term is 0. 1/2 times negative 9.81 is negative 4.905 meters per second squared, times TF, which is 1.4 seconds squared. And if you solve for pi, you get pi is equal to positive 9.6, I think it was 9.61 meters. Any questions about that one? Then the second one is a ball rolling up the ramp. There's a point A and a point B, and those are separated by a distance of 4 feet. And if you do the conversion, 4 feet is equal to 1.22 or something meters. And it says that when it passes point A, the speed is 5.6 miles per hour. And you have to convert that in the problem. What you get is 2.5, yep. 2.50 meters per second. And we know that it takes 1.5 seconds to go from A to B. We don't know that B is the highest point or anything like that. It's just this is like we happen to have someone with a stopwatch at A and someone else with a stopwatch at B. Those are the 2 times we know. And we're trying to calculate first the acceleration. And second, what's the highest point up the ramp? I'm going to do it from A, but if you did it from B or something, I can't complain about that. It doesn't say. But yeah, what's the highest point up the ramp before the ball turns around? Okay, so make our 4 choices. T equals 0, T final, position equals 0, in positive direction. If anybody has any questions about any of the steps, just stop me. Okay, I know I'm going through this sort of fast. So for time equals 0, we'll say the instant the ball passes A. For time final, we'll say the instant the ball passes B. Position equals 0. I'll make that the point A, and we'll make the positive direction go up the ramp. We know that time final, that's given, that's 1.5 seconds. The acceleration we don't know, but that's what we want to find. The position when time is equal to 0. Well, time equals 0 is when it passes A, and the position is 0 at A, so P initial is equal to 0. P final, that's the position when time is TF. That is 4 feet, which is 1.22 meters, and that's in the positive direction from 0, so that's positive. And then V initial, the velocity when time is equal to 0. That's given. The speed is 5.6 miles per hour, so 2.5 meters per second. And that's in the positive direction. And then V final, we don't know, but we don't care. So an equation that works with these, it's the same equation again. P final is equal to P initial plus V initial times time final plus 1/2 A time final squared. So 1.22 meters is equal to 0 plus 2.5 meters per second times 1.5 seconds plus 1/2 times A times 1.5 seconds squared. And if you solve this for A, you get about 2.27 negative. So negative 2.27 meters per second squared. And then for part B, now we're trying to find the ball's location at the highest point on the ramp. So we're going to have to choose, we're going to have to change some of our initial choices. Our time equals 0. We can still make that the instant that it passes B. Sorry, the instant that it passes A. We could do it when it passes B, but let's just not change it. If you don't have to, don't do it. Time final, that's the instant that it reaches the highest point. The position 0, I'm going to make that A again in the positive direction. I'm going to make it up. So a lot of the values are going to stay the same from part A, but any that refer to the time final are going to have to change because we have a different time final. So T final, we don't know that anymore. We don't have a numeric value for that. But if we can solve it without that, that's fine. So I'll leave that off. Now we know the acceleration is negative 2.27. The position when time is equal to 0 is 0. The position when time is TF, that's what we're trying to find, the location at the high point. The velocity when time is equal to 0, VI, is the same thing that it was before. So that's positive 2.5 meters per second. And now we're talking TF happens when the ball reaches its highest point. And when it gets to the highest point, that final velocity is equal to 0. And the equation we can use here is 2a times the quantity PF minus PI is equal to VF squared minus VI squared. So we have 2 times negative 2.27 meters per second squared times the quantity PF minus 0 is equal to 0 squared minus 2.50 meters per second squared. And if you solve for PF, you get 1.39 meters. And then it asks for that in millimeters. So you can think of it this way. 1 millimeter is equal to 1 times 10 to the minus third meters. A lot of people did these conversions backwards. You ended up with, 1 meter is equal to 10 to the minus third millimeters, which is like saying a millimeter is 1,000 meters, But this comes out to be 1.39 times 10 to the third millimeters. Any questions about that one? Okay, and then the third one, an object is launched into the air from a height of 5 feet, and it hits the ground 3.5 seconds later. So that's a ball launcher. The ball's going to go up, come back down to the ground. The flight takes 3.5 seconds. The initial height that it's launched from is 5 feet. And we want to know the velocity of the object at the instant it's launched. So what's the velocity at the launch? And we want it in millimeters per hour. So set up the 4 things. Time equals 0 is the instant that it's launched. Time final is the instant it hits the ground. I'm going to put the 0 on the ground and the positive direction up. Okay, so time final, we're given 3.5 seconds. Acceleration, it's free fall, so this is negative 9.81 meters per second squared. The position when time is equal to 0, P initial, is 5 feet. That's positive. And if you convert that, that is about 1.5 meters. Velocity at time equals 0 is what we're trying to find. And we don't know the velocity when we're at time final. Oh, I skipped one. We do know P final is equal to 0 because after 3.5 seconds after 3.5 seconds it hits the ground. So after 3.5 seconds, the position is 0. Okay, so the equation that'll work is P final is equal to P initial plus VI TF plus 1/2 A TF squared. So 0 is equal to 1.5 meters plus VI times 3.5 seconds minus 4.905 meters per second squared, bless you, times 3.5 seconds squared. And we're just solving that for VI. We get that VI is I don't see it here. Okay, 16.7 meters per second. And then we want it in millimeters per hour. So 16.7 millimeters over hours. Yeah, thank you. Meters. 1 times 10 to the minus third meters is 1 millimeter. Oh, yeah. Stupid mouth and brain not paying attention to each other. 16.7 meters per second. Any objections to that? Okay. Okay, and then 3,600 seconds is 1 hour. And you get about 6.01 times 10 to the 7th, I think. Millimeters per hour. Any, yes?
So I did I did a different equation, and it was marked wrong, but I'm just wondering why, so I set velocity final as 0.
When it hits the ground, that's an easy mistake to make, so everyone should make a mental note of this. When it hits the ground, it sort of seems natural to think that the velocity is 0 when it hits the ground because the ground stops it. But remember, we can only use these equations while the thing's in free fall. So once it hits the ground, those equations don't work anymore. So this only works until the instant before it hits the ground, and at that instant it's still moving down. So if you set the velocity equal to 0, what you're really doing is calculating, what you're really putting into the equation is the highest point the object reaches. The highest point is where the velocity is equal to 0. That's a really common mistake, really easy to make. Any other questions about that? And then the last one So a ball is rolled along the floor and hits the wall 1 meter away. So if this is the start, the ball rolls this way. And it hits the wall after half a second. And then returns to its starting point in another half second. For both of these, it says time equals 0 is when the motion starts. And we're going to plot position versus time graphs. First with the position equals 0 at the starting point and the positive direction toward the wall. And then second, with the 0 position at the starting point, and the positive direction away from the wall. Okay, so in both cases, if this is the starting point and this is the wall, they are how far apart? 1 meter? Yeah. So this distance is 1 meter. And in both cases, what the ball does is start here, go to the wall, bounce off, and come back to where it started. For part A, I'll do A in red and B in green. So for part A, the position equals 0 is here. And the positive direction is this way. And so if the wall is 1 meter in the positive direction from 0, that means the wall is labeled 1. And so what this object does then is it starts at 0, goes to positive 1, and then back to 0. So there's 1 meter. Here's 0.5 seconds. And another 0.5 seconds. I don't care if you draw these rounded or sharp. And then for part B, position equals 0 is at the start again, so there's the 0. But this time the positive direction is away from the wall, which means the wall is in the negative direction. So that means if the wall is 1 meter in the negative direction from the 0, the label for the wall is -1. And so the object starts at 0, goes to -1, and then back to 0. So it looks like this. Any questions about that one? Okay. Well, for sure, if look over your test, and if you think I missed something, it definitely happens. Come talk to me, please, in the next week or something. Not like a month later or whatever, but I'll fix it. And okay. So last time I introduced these, the 6 kinematics equations in 2D. So the 2-dimensional constant acceleration equations for kinematics of a particle. The first pair has to do with the VF equals VI blah, blah, blah equation. So there is now a version for the x components. So it says VFX is equal to VIX plus AX times TF. And one for the y components. So VFY is equal to VIY plus AY TF. So notice that all of the directional quantities are acceleration, the positions, and the velocities. Those all have x and y components, but time doesn't have direction. So we still only have, the only time that's appearing is time final in this. And then the second set of equations is the PF equals PI blah, blah, blah equation. The x component says PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. And the y equation just exchanges all the x components for y components. So PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. And then the third equation is the 2a times the quantity PF minus PI, blah, blah, blah. So the x component equation says 2ax times the quantity PFX minus PIX is equal to VFX squared minus VIX squared. And the y component equation says 2ay times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. So with one-dimensional motion, I listed out a set of steps for using the corresponding equation, so that's what I'm going to do here. This is a general set of steps you can use every time. So the steps for using the constant acceleration equations in 2D. And they look really similar to the ones for 1D, motion along a line. So the first step, we have to make those 4 choices. They're not exactly the same thing, but they're sort of 2-dimensional versions of all the things that we did in 1D. So you have to choose an instant corresponding to time equals 0, an instant corresponding to time final, a location corresponding to the origin, and that origin is the 0, 0 of our coordinate system, and then a coordinate system orientation. The origin location is our 2-dimensional version of the 0 position, and the coordinate system orientation is the 2-dimensional version of our positive direction. And then the second step is we're going to list out what we know and what we want. Now there's more variables. 11 possible variables now. Those are time final, AX and AY, PIX and PIY, PFX and PFY, VIX and VIY, and VFX and VFY. So 2, 4, 6, 8, 10, 11. So this process takes a little longer now. But the goal is the same. We want to find an equation that contains the variable we want and has all other variables known. Okay, so with motion along a line, there was like a step star, like what if this didn't work? And what was that step? Yeah, that was sometimes it's the case that that you need to find an intermediate variable and then go back to step 2. That didn't happen that often, but now it's going to happen most of the time. So now, often, no equation will work. When that happens, solve for TF and then go back to step 2. Really all you're doing is everything that you knew before, you still know what you wanted before, you still want. Now you just know TF also, so you've added one more thing you know. And the reason it's so useful, the reason that TF is pretty much always the intermediate variable we want, is because that's the one variable that carries over from the horizontal motion to the vertical motion. Okay. Okay. There are a few important facts that we're going to use. The first one is if the y-axis is up, and just always do that for free fall. I'm pretty sure all the problems we're doing in 2D are free fall. Then the acceleration vector is 0, negative 9.81 meters per second squared. Or in other words, AX is 0 and AY is negative 9.81 meters per second squared. The second one that we're going to use a lot is that a velocity vector can be found from the object's speed, call it s, lowercase s, and the counterclockwise angle theta going from the positive x-axis to the direction of motion. So if you have this stuff, then the velocity vector is equal to s times the cosine of theta, s times the sine of theta. Okay, so for example, this is the kind of thing, if an object is traveling (15 meters per second) at an angle of 20 degrees above the horizontal, that means that its velocity vector looks like this. It has a magnitude of 15 meters per second. This angle is 20 degrees. And so if that's the coordinate system, then at that instant the velocity vector is 15 times cosine of 20, 15 times sine of 20. And in other words, Vx is whatever 15 times the cosine of 20 is. And Vy is 15 times the sine of 20. Am I going too fast? I am, right? No.
So is the magnitude the 15?
Yeah, the speed is the magnitude. So it'll
So what's the length of it?
the length is the speed. The magnitude is the length of that vector, and it's the speed. So speed is, remember, so in motion along a line, the speed is the absolute value of the velocity. In 2 dimensions, the speed is the length of the velocity vector, the length of that arrow. The third one, only 2 more. At the instant that an object is dropped, the object's velocity vector is the velocity vector of what it's dropped from. So if it's dropped from a car, then at the instant it's dropped, the velocity vector is the same as the velocity vector of the car. If it's dropped from a bridge, then the velocity vector is 0 at the instant it's dropped. And this is the last one. At the highest point in an object's path in its flight, so what was the rule for motion along a line? If something was thrown up into the air, the velocity is 0 at the highest point. So your first thought might be that the velocity vector is equal to 0 at the highest point. There's one that's almost right. But it's really what it is the y component only of the velocity vector is 0. Okay, so what's the deal with that? Why was the full velocity equal to 0 before, and now only one component is equal to 0? So here's a thought experiment that's going to help you. It's going to help convince you. Okay, so thought experiment. Or you can think of this as like, if you don't believe it, here, you do this experiment at home and then you'll be convinced. Okay, so set up like one of those pitching machines. It doesn't look like this, but they don't make them like cannons. But let's say that's what it is. Okay. And this pitching machine, launches a ball, let's say 90 miles an hour. Okay, so do it once, figure out the path of the motion, and then on the second time, set up a ladder and stand up on the ladder So your head is right where the ball's going to go. Okay? So if your hypothesis is correct that the velocity is going to be 0 when it reaches your head, then that ball is going to just gently nuzzle up against your head with no speed, just perfectly at rest. It's going to be a really pleasant experience. But something about that doesn't sound quite right, you know? Right? So the deal is the y component of the velocity is equal to 0 at that point. But the ball still has a lot of horizontal motion. It's still going, you know, close to 90 miles per hour horizontally. And that horizontal motion of 90 miles per hour is going to really hurt. You know, that's the idea. Any questions about that? So try not to make that mistake of thinking the whole velocity vector is equal to 0 at the highest point. It's only the y component of the velocity that's going to be equal to 0 at the highest point. Okay. Sure. Yes. Okay, so these equations say something sort of surprising. So these equations say something surprising. Surprising. And that is that the horizontal and vertical motions are totally independent of each other. Okay, so if you look at these equations, where I'm getting that from is that there's no equation that has both an x component of something and a y component in it. They're totally separated into their own equations. Okay? And that leads to some really weird things, like one consequence is, so imagine one person stands over here, fires a gun. I don't think guns really look like that anymore, but 6-shooter. And someone else stands over here. Boy, that person's a lot weirder looking. Okay, and at the same instant, this person fires a bullet horizontally. And at that same instant, this person drops a bullet. Okay? The gun guy doesn't have to worry about what he's wearing. No one will mess with them. Okay, so if this is true, so this is shot horizontally. This is dropped. This independence of the horizontal and vertical motions says that the bullet that's shot is going to hit the ground at the exact same time that the bullet that's dropped hits the ground. And that doesn't sound quite right. It does, for most people, it doesn't feel quite right. Something's up with that. So these the independence of the horizontal and vertical motions says these bullets should hit the ground at the same time. In other words, this bullet that's shot horizontally, it's going to drop vertically without knowing anything about its really high horizontal speed. You know what I mean? It doesn't know about that. The motion vertically is totally independent of that horizontal motion. So that seems like impossible, but it's actually how it works. And so I want to show a video. Mythbusters did a cool video where they actually really carefully did this experiment. And so this experiment, they're going to set it up where they have a system where this gun fires horizontally at the same time a bullet's dropped at the location where the fired bullet is going to hit the ground. And so you actually get to watch this drop bullet come down and hit the ground just as this shot bullet comes in and hits the ground right next to it. It's pretty cool, and it's pretty counterintuitive for most people that that's the way it works. But that's the way it works, so, you know, I'm just the messenger. Don't shoot me. Okay. One example problem. So what was the message of that video? The horizontal part of the motion and the vertical part of the motion don't see each other. You know, they're totally independent of each other. Okay, so this is like a baseball guy. Are you drawing this? Okay. It's a pitcher. Stirrup socks. Now you know he's a baseball player. Okay, and he throws this ball. His arm comes up, and the ball is released right here. Okay? And at that point, the ball leads with a speed of 20 meters per second, which is actually pretty slow for someone with all this fancy equipment. And an angle of 25 degrees above the horizontal. If it's released from a height of 1.5 meters, how far away horizontally will the ball hit the ground? Okay, so the first step is to make those four choices. An instant corresponding to time equals 0, one corresponding to time final, an origin location, and a coordinate system orientation. Time equals 0, that's going to be when the ball is released. Time final is going to be the instant when it hits the ground. The origin location is going to be on the ground beneath the release point. So that origin location is going to be right here. And the coordinate system orientation is going to be y-axis up. We're always going to do that. And the x-axis horizontal in the direction of motion. So now we're going to list out the variables we know and the variable we want. Now we're going to go through all 11 possibilities. It takes forever, but it's a good habit for now, and then eventually when your hands and brain start doing it naturally, you can stop doing this. But it's a good habit to get into, I think. Okay, so time final. Do we know time final? The elapsed time until it hits the ground? No. Do we want it? No. If we can get by without it, that's fine. What about the acceleration components? Do we know that? Yeah, it's in free fall. So AX is 0. AY is negative 9.81 meters per second squared. How about the position when time is equal to 0? So now this is a vector, and so if you think of the location of the ball when time is equal to 0, that's the star, how far horizontally from the origin do you have to go? Horizontally it's 0, and then vertically you have to go 1.5 meters in the positive y direction. So what you're doing there is you're giving the coordinates of the object when time is equal to 0.
So PIX is 0.
Yeah, PIX is 0.
PIY is 1.5.
Yep, exactly. PIY is positive 1.5 meters. Do we know anything about the final position? We know that it's on the ground, and the ground is is our 0y. So we know Pfy is equal to 0. Pfx is what we're trying to find. We're trying to find horizontally how far away it is when at time final. So Pfx is what we're looking for. Now, do we know anything about the initial velocity? Yeah, we can use that angle and that, we can use the angle and the speed to figure out the velocity. So Vi is equal to 20 times the cosine of 25 degrees and 20 times the sine of 25 degrees. And that is 18.12 for the x component and 8.45 for the y component. So that says that Vix is 18.12 meters per second, and Viy is 8.45 meters per second. And we don't know anything about V final. Is there an equation that works with this? Like we're going to get most of the time with these problems, there's no equation that works. So we want to find T final. So what about T final? Is there one that works there? You can use Pfy is equal to Piy plus Viy TF plus 1/2 AY TF squared. And that says 0 is equal to 1.5. I'm going to stop putting the units in the calculations now, and you can do that too. Viy is 8.45 times TF. AY is negative 9.81, so this is minus 4.905 TF squared. And you can use the quadratic formula for this. That's the C because it's the constant. 8.45 is B. Negative 4.905 is A. And you get that TF is equal to something negative. I don't have it written down. And then something positive, 1.89 seconds. We know time can't be negative, so it's 1.89 seconds until it hits the ground. I'm almost done with this. I know I'm running over a little. So now we can take 1.89 seconds and put that in the known column. Okay, we know all the stuff we did before, and we know one more thing now. And now we can use Pfx is equal to Pix plus Vix TF plus 1/2 AX TF squared. So it says PFX is equal to 0. I'm just plugging in the values that we have in that known column, plus 18.12 times 1.89. And what's the x component of the acceleration? Right, the only non-zero component of the acceleration is the y component. So this term is all equal to 0. And so you get that PFX is equal to 34.27 meters. So the ball hits the ground 34.27 meters away horizontally. Next class, I'm going to just do more examples, maybe the whole time, at least most of the time. But if you have a chance to try to apply this to some of the practice problems, you could do that now. Okay. But if you can't or you don't have time, you can wait until I've done more examples. Yep. Yeah.